The complete material testing laboratory is mainly one part of the material testing laboratory is mainly deals with the strength of the material or resistance to deformation. So what are the different parameters to measure the strength of the material? Can you name few? How strength of the material is indicated for the different material? How strength of the materials are indicated for different materials? Because you are studying mechanics of material, you are studying material science, material testing laboratory. Suppose on steel rod is given, I will ask how strength is, how we can indicate the strength of the material. How can indicate the strength of the material? So one is UTS. You have to specify what is the ultimate tensile strength. So one more is compression strength. There is one more strength. Similarly, tensile strength and compression strength, there is one more strength when that is referred as a torsional strength. Because torsional strength will come into picture only when the materials are subject to torsional loading. Suppose in some cases materials are subject to combined torsional loading as well as the tensile loading. Can you give an example? Combined torsional loading and tensile loading. One example. What about fan rod? Is subject to only tensile loading or torsional loading? It is subject to both because there is a self weight of the fan. Because of the self weight of the fan, it is subject to tensile load because it is pulls the fan rod will try to the fan weight because of the self weight of the fan it will try to pull the fan downward direction. So when fan is switched off, then it is subjected to only tensile loading. But when fan is switched on, then it is subject to combined loading, both tensile as well as the torsional loading. There are some cases, combined loading cases out there. The later stage of your engineering course, you are going to study combined loading. So there are different failure theories also there when when components are subject to combined loading. So applying tensile test as well as torsional test as well as bending test simultaneously, it may be very difficult. Either we can conduct only torsion test, or either we can conduct only tensile test, or either we can conduct only compression test. From those values, by using some hypotheses or theories of failure, so we can get what is the strength of the material when it is subject to both tensile loading as well as torsion loading. So then we require torsion strength of the material. So then there is a one more, how we can specify the deformation, resistance to deformation. The resistance to deformation is normally specified in terms of the Young's modulus. When it is subject to tensile loading, it is referred by Young's modulus. When it is subject to torsion loading, then there is one more constant that is referred as the rigidity constant or rigidity modulus G. So as per our experiment is considered, in torsional test, you have to find out, so what is the modulus of rigidity or rigidity modulus? That is the major aim of our experiment, conduction of the experiment for the torsion testing. Then the same material may be subject to yield strength also. You have to find out yield strength of the material also. For that, you have to find out torsion yield strength of the material. So one more is modulus of rupture. That we have the formula, we can find out. Then if you consider those are the specification, those are the specification I don't read. It is anyhow, it is available in your what is the clearance between the grips, what is the torque range. We can apply the torque from 30 Newton meter to 60 Newton meter. Maximum torque capacity, how much amount of torque we can apply from the machine is maximum we can apply 60 Newton meter. Those are the maximum amount of torque. This is our actual torsion testing machine. ಹಲೋ ಚೆಕ್ ಮಾಡ್ತೀನಿ ಲ್ಯಾಬ್ ನಡೀತಾ ಇದೆ. So this is our actual torsion. You can see the videos, then you'll understand better. So this is the basic concept of torsional theoretical concept behind torsional testing. So So can you tell what is the torsional equation? One of you can tell what is the torsional equation? What is torsional equation? What is torsional equation? You studied torsion in your material, in your mechanics of material? Yes or no? So now torsional equation is tau by r is equal to T by J. That's equal to G theta by L. So whenever material is subject to torsional loading, the stress induced in the material is shear stress, not compression stress or bending stress. It is shear stress, where R refer to radius of the shaft, T refer to how much amount of torsional load you are applied, J refer to what is J? J is given by pi d power 4 divided by 32. So G is the rigidity modulus G. It is equivalent to Young's modulus. Young's modulus is mainly gives what is the resistance to the deformation when it is subject to loading. Normally either tensile loading or compression loading. But G refers to the resistance to torsional loading is referred by G. Into theta, theta is the torsional, it is rotation. How much amount the shaft is rotated, one end of the shaft is fixed and whatever the other end, or if both ends of the shafts are slightly twisted, then we require T1 and T2, that is theta. L is the length of the shaft. This is the torsional equation. As per your T, how much amount of torque you have to, as per our diagram is considered, the formulas are considered. T is known how much amount of torque we are applying from the instrument or torsion testing machine we can get. J is the polar moment of inertia. We know the diameter of the specimen. From that we can get polar moment of inertia. Then pi d power 4, that is the polar moment of inertia. Then J is known. Theta is known how much amount it is rotated, that you have to note down. The length of the shaft is also known. If you consider those right side of the equation, T is known, you have to note down, that is observation. T is observation. Theta is your observation during your experiment. So L is the initial dimension you have to measure. J, by measuring initial diameter, we can get the value of J. Only two observations you have to make. One is how much amount of torque is applied, you have to note down. There is an indicator, pointer. From the pointer, you can you note down the torque. And theta is the rotation. There again, there is one more device, the regular analogous device or pointer. From that, we can get the value of T. And from that, we can get the value of G. So this is the concept involved in torsion testing machine. I thought that you studied about torsion in your... So now notation, tau is, any of you are familiar, is a shear stress, R is the radius, and torque we can express in terms of Newton mm most of the time. J is the second polar moment of inertia. G is the modulus of rigidity. Theta is the angle of twist. L is the length. Then procedure I will tell you. When you come to observation, so one is material. What type of material you are selecting, whether you are selected for steel material, whether you have to determine torsion strength of the steel or copper or aluminum, you have to note down. So we are given the steel specimen. You have to note down the diameter of the specimen, that is the observation part. The length of the specimen is also required because those equations, in the torsion equation, you have to use length of the specimen. Gauge length of the specimen also you have to use. And torque, maximum torque applied also you have to note down. And we require vernier caliper, least count, it is given in the vernier caliper itself. So this is the tabular column. So these values will be given. The torque, so from the equipment, you are getting the torque in terms of Newton meter. You are getting angle of twist in degrees, that you have to convert into radians. Later stage, you have to convert into radians. Then finally, you have to plot the graph of torque or torsion loading versus degrees of or angle of twist. It is nothing but a load versus deformation. The load is torsional loading. The deformation is angular deformation. Compared to your bending, tensile, and other tests. So in the case of torsional tests, the loading is torsional load, torque. The deformation is angular deformation. We are getting in terms of theta, or either we can get in terms of degrees. So again, by knowing the polar moment of inertia, the D, The diameter of the specimen, you can get the value of J. You are familiar with this, even you studied those formulas in first year also. The polar moment of inertia J is equal to pi d power 4 divided by 32. And G is modulus of rigidity, that is given by T theta into L by J. L is constant for the given specimen. J is also constant. So T by theta is nothing but a slope of the graph. You have to plot the graph of T versus theta. So that that is nothing but a slope of the graph. If you multiply a slope of the graph to L by J, then you get rigidity modulus. Then modulus of rupture, we know the TF final torque divided by J into R. Yield strength. So when shaft yields, it is almost like a yield load divided by J into R. R refers to radius. So this is a brief discussion of the formulas. What I'll do is I'll show one video that is equal to Vickers hardness test or dye penetration test. Then I'll explain other part. Theory part I'll explain later. So what I do is there are two types of testing. This is a totally different test. There are two types of test. One is destructive testing, and one more is non-destructive testing. So this is comes under destructive testing, non-destructive testing. It is nothing but a dye penetration testing. So dye penetration testing is comes under non-destructive testing. That one point you have to remember as per this test is considered. Again, on the workpiece, there may be crack may be present on the surface or inside the surface, but your dye penetration test will detect the crack only on the surface, not subsurface crack. If the crack is present at 5 mm depth or 2 mm depth or 3 mm depth, then it will not detect. So first see the video, then I'll explain how exactly there is a theoretical fundamentals with respect to our PDF file. I'll explain the basic theoretical concept. In general, you are applying penetrant. Imagine you have the cast workpiece. You are applying dye. That's why it is referred to dye penetrant. It is a red color. So if the red color dye goes into the crack because of capillary action, then you have to clean the surface, top surface. So then dye is present only inside the crack, that we can detect, or by visual the checking only we can identify whether crack is present on the surface or not. Mainly it is used to find out whether crack is present on the surface or not. Before that, as usual, you have to go for cleaning the surface. Then you have to apply the dye or penetrant. After applying the penetrant, then you have to remove the penetrant by applying, there is one more chemical that is after the developer. So after removing the developer, everything, then end with only on the cavities only there is a dye, the red color dye. Wherever there is a red color on the surface, that indicates that on those region there is a crack. I'll first see the video, then I have some schematic sketches to understand how exactly DPT works. First see the video. Is it video is visible? Is it video is visible? Oh,
Yes, sir.
no or yes?
Yes, sir.
Yes, sir.
So first one is you can see the developer. It is white. There is a penetrant. This I think. So here you are conducting a test for two specimen. One is cast specimen. During casting also there may be crack on the surface. During welding also, especially you are talking about the arc welding. During welding also there may be crack on the surface. On the surface, those things. Two specimen you are testing. One is welded specimen. One more is the cast specimen to find out whether crack is present or not by using dye penetrant test. So remover is mainly for cleaning the surface. So that's why it is referred as a remover. If there's a dust or oil, etc., present in the specimen, because during the foundry operation also you are familiar, there may be sand particle or there may be mud, all those things, foreign particles, or sometimes greases, etc., that can be removed by remover. Not by initially you have to go for washing also. Afterward the washing, you can go for remover. So you are using the term penetrant. You know what is penetration. So we have a cavity. So when your penetrant is applied, red color penetrant is applied, because of the cavity, the capillary action, you studied those capillary action in your physics, etc. So there may be small crack because of the capillary action, this penetrant will penetrated into the small crack. That's why it is referred as a penetrant. It is red color. Penetrant is always red color, so that we can identify wherever there is a crack on the surface. After removing the developer, etc., we'll get only red color. On those regions, we can conclude that there is a crack. So developer, you are after applying penetrant, you are applying developer. On the top, it is a white color, it is a contrast color. So then you have to remove the top developer. So then end with only the penetrant. So now to remove the dirt particle, the foreign particle, grease, dust, etc., first you have to clean the surface. For the cleaning the surface, you are using the remover. This is the application of remover. This is a welded specimen. There are two specimens. One is cast specimen and one more is welded specimen. You are going to find out. There is no formulas. There is no calculation here. After conducting the test, only one conclusion. I not give any observation for this. Everything is there in your manual. Only one conclusion you have to write. The test is conducted. The DPT test is conducted, and concluded that there is a crack in the cast specimen as well as crack in the welded specimen. That is the conclusion. No data will be given for DPT. Interesting. So now you are applying the red color penetrant. Now you are applying the red color penetrant to the welded specimen. So there's a contrast color between penetrant as well as developer, because penetrant is red, developer is white. So once you remove the developer from the surface, we end with only the penetrant in the crack only, not in any other surface area. Now we applied the penetrant. So there are some schematic diagrams are there from. So now we can see after application of the penetrant, we can see the crack. Not macroscopic crack, even microscopic crack also we can observe once the penetrant is applied. So you can also even casted part, if it just without applying penetrant as well as developer, if you observe the casted part, it looks very smooth surface. But only application of the this penetrant as well as developer, then only you can identify the crack present on the surface. So we can see how nicely we can see the defect only once we apply penetrant, only then we come to know the defect. So okay, one more video I'm showing, just I'll set. I have to download from my mail. Just wait. Next is torsional video. One minute, I am opening the video. Just I am opening the video. You will not be able to see the video. Is it video is visible? Is it video is visible?
No, sir.
No, okay, okay. Just wait, I am downloading it. Just wait, I'll download, and only once it is download, and if you open from our desktop, then only you can share it. Before that, I'll finish one more experiment. Then we'll open this. I'll open this. I hope this video is visible.
Yes, sir.
Okay. Just before going for this, I'll give a brief introduction. Then I'll have regular schematic sketches and Word document, the PDF document to understand the concept. Already we have finished two tests, hardness test. One is Rockwell hardness testing, where depth of the indentation or penetration is measured, and depth of the penetration or indentation is directly proportional to the hardness. So internally, some mechanism is there in the this Rockwell hardness testing machine. So it will measure automatically to measure the depth of the penetration, and there is some proportionality between depth of the penetration and hardness number. There is a digital indicator. It is calibrated, the regular indicator or pointer. It is calibrated such a way that directly it gives the hardness number. In the case of Rockwell hardness testing machine, it gives the directly hardness number or Rockwell hardness number. But inside, what is happening is it will measure the depth of the penetration or depth of the indentation. That is in the case of Rockwell hardness testing. That already you have finished one more test. So that is nothing but your Brinell hardness testing, where diameter of the indentation is measured. You are using the diameter. So once you don't know the diameter, there is a formula. So complete test in Brinell hardness testing machine is only one observation you are making. So your the indenter diameter is fixed. It may be 5 mm or 10 mm. The load is also fixed depending upon the material and indenter diameter. Only one observation you are making in the case of Brinell hardness testing is you are measuring the indentation diameter. There is a difference between indenter diameter and indentation diameter. The best example is, imagine you have a cricket ball. The diameter may be around 3 to 4 inch. Diameter may be 3 to 4. Let me 4 inch. If you dip into the cake, so then if you apply a little amount of effort, if you dip into the cake, so in the cake also you will get one spherical shape. That diameter may be, instead of 3 inch, it may be only 1 inch. If you apply a slight amount of load, the diameter in the impression on the, we have the cricket ball, it is impression on the cake. That impression diameter may be only 1 mm, 1 centimeter, 1 inch, or it may be 2 inch. How much amount of force you are applying? If the indentation diameter is more, means that it penetrated more into the cake. That means cake is soft. That's why it goes more into the cake. If the instead of cake, if you keep some soft metal, or let it be aluminum only, instead of 1 inch or 2 inch, it may penetrate only 0.1 mm or 0.2 mm. So everything is depending upon how much material penetrate or indenter penetrated into the material. If the soft material, so it will penetrate more, like aluminum is a very soft compared to steel. For the given loading, the aluminum material and the indenter penetrate more for the aluminum compared to the steel. Compared to ceramic material, there is a very less penetration. So finally, we are measuring the indentation diameter in the case of Brinell hardness testing machine. Diameter you are measuring. In the similar way, there is a one more material, the one more testing machine. It is referred as Vickers hardness testing machine. Because once ball is the indenter is spherical, the specimen may not get deformed. It is referred as local deformation. If I apply tensile load, whole specimen may extend. If I apply compression load, the only part of the specimen, the whole specimen may compress. But when in the case of hardness testing, the only localized the deformation takes place. That's why the basic definition of hardness testing is it is a property of the material which oppose or resist the localized plastic deformation. Now, when if material is very hard, like a ceramic material or high carbon steels or high tool steel, the material is very hard. Then, if you use ball indenter, material may break also. If you suppose you want to find out the hardness of the glass, if we apply the load by using spherical indenter, glass may break. In such cases, instead of using a ball indenter, you have to go for the diamond indenter. Diamond cone, normally referred to the diamond cone indenter, so that once you apply the load on the diamond indenter, the impression on the specimen may not be your circular, so it may be diamond, or it may look like in the top view it looks like rhombus. So that diameter you have to find out. We have the diamond indenter, diamond shaped indenter instead of saying diamond indenter. So when load is applied, we will get indentation. It is almost like a rhombus when you see from the top. The rhombus means we have a major diameter and minor diameter, or both diameter may be same. If you are able to measure the diameter 1 and diameter 2, and if you take the average value, then we'll get, we have the formula similar to Brinell hardness testing machine. We can get the hardness number. In simple way, in simple one statement, we can say that in the case of Vickers hardness testing machine, we are not measuring the diameter of the indentation. You are measuring the diagonal length of the indentation. Two diagonal length. So diagonal length one is referred to diagonal one is referred to D1. The diagonal length 2 is referred to D2. So finally, you are taking D1 plus D2 divided by 2. That is the average diameter of the rhombus or indentation. Once you substitute average diameter of the indentation, then we can substitute in the formula. We can get Brinell Vickers hardness number. That's the basic concept. So again, you have to mount the indenter using Allen key. Almost construction, mounting the specimen, table, everything is same. The difference is how you are measuring the diagonal length. You are using special microscope for the special arrangement for measuring the diagonal. There are two measurement you have to make. One is diagonal diameter. For measuring one diagonal, we have 1 micrometer like arrangement. Find out the diagonal. Those diagonal lines, the diagonal lines, imaginary diagonal lines are perpendicular to each other. There is a 1 more micrometer to measure the diameter from the other side. After measuring the diameter from the 1 micrometer, you have to rotate and you have to measure the other diameter, like a rhombus, other diameter length by using other micrometer. It is almost like a micrometer only. Now you are making the indentation by application of the load. The first part, you have to apply the load, you have to make the indentation similar to the previous case. Now this indenter is here. Then afterwards, once indentation is over, you have to rotate this, indenter goes to other position. Then in this position, we'll get lens and focusing system and lighting system so that we can observe the indentation from the focusing or lighting system. So once you apply start button, then only load is applied. So why you have to hold it for a few seconds is, if you just apply the load, it will not undergo deformation. That's why some fraction of second is required to undergo plastic deformation on the specimen. That's why you have to hold the start button for a few minutes till you get yellow light. There are two micrometer like arrangement, because you have to measure the two diameters. One is major diagonal and one more is minor diagonal. For that, there are two micrometer like arrangement. You have to, from that arrangement, we can see, because definitely before going for the lab examination, definitely there may be some repetition classes. In that time, we can see all the minute details, experimental, practical. Now you are applying the load. You are not measuring any diameter. So once sufficient load is applied for a few seconds, the light will be on. Then you can stop application of the loading. That indicates that already sufficient deformation is already there in the specimen. You have to, because one end of the diagonal, suppose we have the diagonal line, one end of the diagonal reading will be, that will be R1. Other end of the diagonal reading is R2. R2 minus R1 gives the diameter. Like, so imagine one end of the steel rod, the dimension by measuring scale, it will be around 1 centimeter. If the other end of the steel rod, the dimension in the scale shows 2 centimeter. So 2 centimeter minus 1 centimeter gives the diameter of the steel rod. In the similar way, here also it is measured. So we can see, I think, the indentations are very small. You can see here, this is a small indentation. Especially it is used for ceramic materials and hardened steel, hardened cast iron, some hardened even copper also. Only for harder material, diamond indenter is used. Diamond cone indenters are used in the case of wicker hardness testing machine. Otherwise, the specimen may break. So you can see the indentation. It is done by your senior from the last few years. So in conclusion is, I'll stop the video. The conclusion is, in the case of wicker hardness testing, the indenter is diamond indenter. After indentation, if you use correct technical word, after indentation, you are measuring the major diagonal of the indentation and minor diagonal of the indenter. That is nothing but D1 and D2. D1 plus D2 divided by 2, that gives the diameter, the diagonal length of the indenter. So by substituting this in the formula, it is given in the manual. So we'll get the wicker hardness testing. Then we'll go for one more, this torsional testing. Just it is not download. Video is already downloaded. We'll see how it works. Video. Can you see the video? Yes or no? Can you see the video?
Yes, sir.
Okay. In simple, in torsion testing machine, other than construction of the machine, etc., procedure, etc., you have to measure two parameter. One is you have to apply the torsion load on the specimen. That is nothing but torque. Your one observation you have to note down is torque. So one more observation you have to note down is the how much amount of deformation occur. It is nothing but a angular deformation. Once you know T and theta, you have to plot torsion torque versus theta. The slope of the torque versus theta multiplied by L by J, that gives the rigidity modulus. Once you substitute the slope in the rigidity modulus equation, we can get the rigidity modulus. Major purpose of this experiment is to get the rigidity modulus. The rigidity modulus is throughout your engineering course, 4 year, or if you join mechanical industry. So throughout your professional, you are talking about Young's modulus, rigidity modulus. What is the material? Once you say material, what is the Young's modulus? What is the rigidity modulus? Or whether rigidity modulus changes or Young's modulus changes. Most of the torch shaft material, so they should have higher rigidity modulus because shafts are subject to torsion loading, like your fan rod. Fan rod is also subject to tensile loading as well as the torsion loading. Initially, you have to measure the diameter. Diameter measure is required for finding out the polar moment of inertia. It is used in the. So you have to measure the angular rotation. For that, there is a degree. You can note down initial value and final value. From that, we can get how much amount the material undergo torsion. So now the original shape is 10 mm by 10 mm square bar, but torsion load is applied only for the circular section. The here square section is used for holding the specimen. That you have to remember. It is not your specimen is not a square cross section. Actual gauge length, in the gauge length area, the specimen is the circular cross. This circular in nature, not square. The square part on the left hand side and the right hand side, it is used for gripping purpose. Purpose is if it is a square section, holding will be easy. If it is circular section, there may be slips also, because if slipped by 1 degree or 2 degree, your Young's modulus may changes. You may not get the correct Young's modulus. Why diameter you have to measure is the J is given by pi d power 4 divided by 32. For that, we have to find out the polar moment of inertia or second polar moment of inertia. We require the gauge length is again required for finding out the rigidity modulus. Rigidity modulus is given by T by J into L by L by this one more J. That's why you require L is fixed for the given specimen. J is also fixed for the given specimen. J is depending upon diameter. So L also required. Once you multiply those parameter into the slope, you will get the rigidity modulus. First, you have to mount the specimen properly in the jaw or gripper. Then only you can apply torsional load. This indicates how much amount of torsional load is applied. So up to 60 maximum loading capacity is 60 Newton meter. Even scale maximum loading is also 60 Newton meter. Don't imagine 25 to 30. Between 25 to 30, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 divisions are there. So that means each division refer to 0.5 Newton meter. Each division, bigger two lines are there that refers to 0.5 Newton meter.
Newton meter comes to 0. This is supporting. After 3, so you set it to 0. You set it to 0.
Initial angular deformation you are setting to 0. This what is scale mentioned here, that is the angular deformation. You are applying the torsion loading. Once you apply torsion loading, the torque shaft rotates by some degree. You are fixing for the one. That means to get angular deformation of 2 degree, how much amount of torque? It is almost like a load versus deformation diagram. A load versus deformation values. Here load is torsion load. The deformation is angular deformation in terms of degree. The load is in terms of Newton meter. That's all, no difference. through the motor you are applying torsion load. So once it crosses the rigidity modulus or torsion strength, the specimen. Don't think that specimen breaks, that rotates. That specimen is twisted. You have to remember, the specimen is going to twist. It is not like a specimen rotation in the case of fatigue testing. Because one letter of the specimen is fixed. So that's why specimen twists or it undergo torsional deformation. It is not like a fatigue testing machine where specimen rotate, but here specimen will not rotate. One end is fixed, another end is rotated so that there is a angular deformation of the specimen. During this process, how much amount of torque is applied, how much amount of deformation occur, those 2 points you have to. No. Now you can see the specimen is already broken. Now you can see the specimen is going to break now. Specimen is going to break now because of torsion loading. So now you can see the specimen is already broken. That is the TF value. What is the torque? The maximum amount of torque the specimen can take. That is the maximum load taken by the specimen is around 45.52. You can say that is around 45.6. We can say that is the maximum load taken by the specimen. That is nothing but a TF. What formula you are. Okay, if you have any doubt, especially torsional testing machine will share the information observation, and Vicker hardness testing, not Vicker, Vicker hardness testing observation and values will share. And tomorrow or day after tomorrow, I am sharing in your Google Classroom as well as in the class group. So that you start, those who have finished, they start writing the record. I think shortly next week we're going to conduct another 1 or 2 tests. Then that will complete your MT lab testing. Only next one more test left out is heat treatment. Other than heat treatment, there is a one more ultrasonic flaw detection. It is non-destructive testing. It is only for a demonstration. You can see the demonstration, but you have to write everything information in your record. If you have any doubt, you can clarify now. So please answer your attendance. I'll call your names and the number before ring instead of noting down, searching for your number. Hey, I think those who are not edited your USN number, please edit your USN number and name. One, two, three, four, five. Only 5 students are edited your USN number. Around 12 minus 1, 11 students are here. Others edit your USN number. Not 12, I think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think all are entered your USN number. Those who entered your USN number, we can, if you have any doubt, you can clarify now. If you don't have doubt, we can leave. I'll go for. I hope everyone has entered your USN number.
Yes, sir.
Make sure that you entered your USN number. After, don't say that I was present, I was not, because once I stop the recording, then your USN number will not be recorded. If you have the doubt, you can don't enter twice or try, just you check in the chat box. Then you, if your name is not entered, then only enter. Otherwise, don't enter. If there are some few students, to be on the safer side, they take extreme precaution. They'll enter it once or twice. Make sure that they have entered their name. Just if you can scroll your chat box, you can find out whether you entered or not. If you already entered, no need to enter it once again. Otherwise, I require some more time to check whether you entered once, twice, or once. If you have any doubt, you can clarify now. Otherwise, you can leave the class. I'm going to stop recording.